Hello students, in this session we are going to study the Illo's theory of column, both ends fixed. So condition is like this, I am making here that this is one end, it is fixed and this is our column initially, and we have applied a load to this column right, and there is some deflection in the column like this, right? And you know that at this point some part is horizontal because theta is 0 at this point, slope is 0 at this point and theta is 0, right? And we want to find out the deflection. Suppose this is the point where we want to find out the deflection y, and this is the distance x. This is it. So what is this safe P load using the Euler's theory of column? And you know that suppose this is the length L, and you know the boundary condition in this case. What are the boundary condition? This end is fixed as well as this end is fixed, and this is the some part theta is 0 and y is also 0 at this point. So what is boundary condition for this? Boundary condition. So boundary conditions are x, when x is 0, y is 0, right? So first boundary condition is x equal to 0. At that point deflection is 0. Another is at x is equal to 0, that slope because this is a fixed point, right? The slope is 0. So x is equal to 0, slope dy by dx will be equal to 0. One more condition can be used if required, that x is equal to L. At this point also again y is equal to 0. So x equal to L, again y is equal to 0, and also at x is equal to L, again the slope at this point is also 0. So at x is equal to L also dy by dx will be equal to 0. So this is the boundary condition. Whatever required you can use the boundary condition in this case here, right? Now we want to find out the Euler's load, this, right? So first we have to find out the deflection equation, and using that deflection equation we will find out the load P. So what is deflection equation? You know, deflection equation is given by EI d2y by dx square will be equal to movement, bending moment, and you should know that at this point also there must be some movement because there is a resisting bending moment at the fixed points also, right? So this is, suppose here it is anti-clockwise, here it is clockwise, so this is a resisting bending moment M, right, at the fixed ends, both ends fixed, and suppose this point is C, this is point D, and this point is E, right? So find out the deflection equation, the moment due to this load P and this moment M, how it can be given. You know that this is concave towards the initial central axis. About central axis, this is a concave curve, and concave curves, this is the negative bending moment at this point according to our sign convention, right? So you can see here this is a concave curve, right? So or you can see it is a clockwise, on left side it is a clockwise curve, right? So clockwise left side is a negative basically, right? So P multiplied by y minus P multiplied by y, negative, and this is anti-clockwise, M is anti-clockwise, so M can be taken as positive then. So bending moment M is positive. So there are two loads basically at the fixed end. One is P, which is this load P, applied load, and one is resisting bending moment M, this M we have taken. This is clockwise, and we take on left side clockwise is if it is negative, then anti-clockwise should be positive, so that's why we have taken it positive, right? Solve it somewhat so that we can give a simple equation. So d2y by dx square, this py can be taken here, p by ei y will be equal to m by ei, like this, right? Let us assume that this p by ei is m square. Let p by ei equal to m square. P by ei is equal to m square. So d2y by dx square plus m square y equal to m by ei, isn't it? Right? Or from this equation you can also write that p by ei is m square, so ei will be equal to m square p, and p by m square, so ei can be written as p by m square. So from here you can m by ei can be written as p by m square. So you can also write this as p by m square, right? P by m square, this ei, and it will be reversed, so this will be m uh, p by this ei will be equal to p by m square, so p that will be equal to, leave it, remain it as it is, right? P m by ei, right? So this is the equation which is to be solved, right? This is first equation, and this is double derivative, and double derivative it is to be solved, right? So this is the equation which we have to solve, right? So what is the solution of this equation? That is equal to y is equal to some constant a sine mx plus b cos mx plus this term divided by m square, so this term m by ei multiplied by m square, right? So this is the solution, that a sine mx plus b cos mx plus m by ei m square, and what is m square? That is p by ei, so this will become m by p. So y will be equal to a sine mx plus b cos mx plus p by ei, p by m plus p by m, m by p, m by p, m by p. So this is the equation to be solved, this equation. This is the solution. This is the solution of this differential equation. This differential equation has this solution, m by p. M square we have put here, p by ei. So this ei cancels, so it will be m by p, right? So y is equal to a sine mx plus b cos mx plus m by p. So this is the equation which need to be solved, right? Now what else? Put the boundary condition. First boundary condition is x equal to 0, y is equal to 0. X equal to 0, y equal to 0. Put this boundary condition. So first boundary condition is, boundary condition 1 is x equal to 0, y equal to 0. Put here, you will get 0 is equal to a sine 0 plus b cos 0 plus m by p. Sine 0 is 0, cos 0 is 1, so b will be minus m by p. So b will be equal to minus m by p. B is equal to minus m by p. So this is the value of b, minus m by p. Second boundary condition 2, that is x is equal to 0, slope is also equal to 0. So x equal to 0, dy by dx will be equal to 0. But what is dy by dx? From here, dy by dx will be equal to am cos mx minus bm sin mx. So am cos mx minus bm sin mx. So this is the slope of this equation y. So this is suppose equation number 3, right? So now dy by dx is 0 at x is equal to 0. Put here, you will get 0. What you are getting is 0 will be equal to am cos 0 minus bm sin 0. Sin 0 is 0. M cos 0, m cannot be equal to 0, so a should be equal to 0. From here we can find out that a is equal to 0. So this is the new constant found out, a is equal to 0. put in this equation number 2. Put in equation number 2, what you are getting is, put this into, also put in this into a is equal to 0, b is equal to minus m by p. Put here a equal to 0, b is equal to minus mp. What you will get, that y is equal to, you will get the new equation, sine 0, a is 0, a is 0, it will become 0, b cos mx, b minus m by p, so minus m by p cos mx plus m by p, right? So this is the new equation. And at x is equal to L, y is again 0. Put third boundary condition that x equal to L, y equal to 0. Put here 0 will be equal to minus m by p cos ml, minus m by p cos ml plus m by p. So from here you will get m by p will come here, cos ml equal to 1, cos ml equal to 1. And at what value of cos the cos theta is equal to 1? At what value of cos theta is 1? That is at cos 0 or cos 2 pi, right? So we are taking first non-zero value, that cos ml will be equal to cos 2 pi, because value of 1 is cos 2 pi, right? So from here you will get ml will be equal to 2 pi, or m square L square will be equal to 4 pi square. M square we know, p by ei. Put here p by ei L square will be equal to 4 pi square. From here you will get the Euler's load as 4 pi square ei upon L square. So this is the Euler's load, and this is very important, you have to remember it. Euler's load for both ends fixed, that these are the boundary conditions. This is the condition that these are fixed and it will be having a load P and the moment M. We have applied our deflection equation. This is the deflection equation, and solving this deflection equation we got the deflection curve y is equal to this. Finding the y, we know two constants a and b to be solved. We utilize the boundary conditions. First boundary condition we have used, that found out that b is equal to minus m by p. Second boundary condition applied and we got that a is equal to 0. Again apply this boundary condition, value of b and a in this equation 2. You will get this equation, y is equal to minus m by p cos mx plus m by p. Third boundary condition, utilize this third boundary condition, that x is equal to L, y is equal to 0. Put these values here. What you are getting is, from here you are getting the Euler's load. Finally you will get the Euler's load for both ends fixed.